This is section 1.7, inverse relations and functions. Your I can statements for this section. I can use the horizontal line test to determine inverse functions, and I can find inverse functions algebraically and graphically. An inverse relation is just a relation where the x and y values are switched. In an equation, the inverse relation can be found by interchanging the independent and dependent variables. So to find the inverse function, you just switch your x and y and then solve the equation to get y by itself again. The inverse relations are reflections of each other across the line y is equal to x. So if this is our table of our original function, our function is y is equal to x squared minus 4. We have our x values and our y values. To find the inverse, if you have your table, all you're going to do is switch your x and y values. So over here we had an x value of -3, a y value of 5. Our inverse, we switch that. Now our x is 5, our y is -3. To find that algebraically, you're going to take your equation and you're going to switch where the x and y values are located, and then you're going to solve the equation to get y by itself. Graphically, when you're done, it is going to be reflected across this line of y is equal to x. So an inverse function is just the inverse relation of a function, and you're going to denote it with the little -1 up there, so that's the inverse of f. So if f of x is equal to x plus 4, the first thing you're going to do is you're going to switch this so it's a y so you can solve it. To find the inverse, you switch your x and your y values, and then you want to get the y by itself. So I'm going to subtract 4 to the other side, so x minus 4 is equal to y, and then we would denote that as the inverse function of x is equal to x minus 4. So if your original function is x plus 4, the inverse in this instance would be inverse function is x minus 4. We know we're going to have an inverse function if on your original function we can do a horizontal line test and each line only touches the graph in exactly one place. Remember, we know it's a function if you do the vertical line test, but to check for an inverse, you will check the horizontal line test. So we're going to graph the function using our graphing calculator, and then we're going to apply the horizontal line test to determine whether the inverse function actually exists, and then we're just going to say yes or no. So first we need to graph our function. If you remember, this value is inside the absolute value, so it means it's attached to the x. When you pull it out, you're going to change the sign. So that means my center of this graph will be at +1 and 0. So instead of starting at 0, 0, we're going to start at 1, 0. And it has a slope of 1 because it's the absolute value function. We're not multiplying by anything. It's going to go up 1 over 1 in each direction. Once you have your graph drawn, you will do the horizontal line test. So you're going to draw a horizontal line. If it touches the graph in more than one place, there is no inverse. So for this function, there will not be any inverse because it touches the graph in 2 places. If we graph this one, we're going to go ahead and graph this one on our graphing calculator. On your calculator, your graph should look something like this. So once you have a graph, you're going to do your horizontal line test. And anywhere on this graph that I were to draw a line, it is only touching that graph at one spot. So there is an inverse for this function. 1-to-1 is a function where no values of x is matched to more than one value of y, and no value of y is matched to more than one value of x. If a function is one-to-one, then there will be an inverse. The domain of the function will equal the range of the inverse, and the range of the function will equal the domain of the inverse. So if we think of a quadratic, for each y value, there are two different x values, because if we graph it, it looks like this. It's symmetrical on both sides. So if I have a y value of 2, there are two different x values that go along with a y value of 2. So that is not a one-to-one. It would not have an inverse. But if we think of a cubic function, for each y value, there's only one x, and for each x value, there is only one y. So that is a y to y, one-to-one, function. So there will be an inverse. The domain of this function will be the range of the inverse, and backwards, the range of this function will be the domain of the inverse. To find an inverse function, I showed you one of these, an easy one of these before. You're going to determine whether the function first has an inverse. Then for your equation f of x, replace your f of x with y. Then exchange your x and y values. You're going to solve for y. Once you get y by itself, then you'll replace it with the inverse function of x. And then we're going to state if there's any restricted domains for our inverse function. Remember, your domain is the range of the first, or your original function. So if we look at this function, the first thing we need to pay attention to is what is its domain and what is its current range before we do anything else. Then we're going to decide if it has an inverse. So our domain, what x values can you put in? To be able to take the square root, it has to be 0 or larger. So x has to be greater than or equal to 0 when we're done. So we know x minus 4 has to be greater than or equal to 0. To get the x by itself, our domain, x is going to have to be greater than or equal to 4, so that value is 0 or greater, so we can take the square roots. When we find the range, what values can come out of this? The range can only be values that are 0 or greater, so our y values have to be greater than or equal to 0. Because when you take the square root, we're looking to see what values are going to come out. When you take a square root, the answer is always positive, or it could be 0. So our range, y has to be greater than or equal to 0. So when we're done finding the inverse, if there is an inverse, then the new domain, the x's, will have to be greater than or equal to 0. If you graph this function, it will look like this. So if we do our horizontal line test, it is going to touch only one place, so we can find the inverse. So the first thing we're going to do is we're going to replace f of x with y. Then we're going to switch where the x and the y are located to find the inverse. Once you have them switched, you're just going to use your algebra skills to get the y by itself. The first thing we need to do is we need to get the square root out of it. The opposite of square root is to square both sides. After we've squared both sides, we need to get rid of that 4. Right now it's a negative 4, so to move it to the other side, we're going to add it. Now that we have the y by itself, we're just going to replace that y with the inverse function notation. So we have the inverse function of x is equal to x squared plus 4. Now we have to state the domain and the range. Now if we look, this looks like we should be able to put in any value of x and still get a y value. But we have to go back up to the range of your original function. And remember, the range of your original function is the new domain of your inverse function. So our domain in this case is going to be x has to be greater than or equal to 0. So if we take a look at another one, first thing you need to do is you need to graph this function and make sure that it can have an inverse by doing the horizontal line test. And after graphing this one, it does have an inverse. So we're going to find the domain and the range of the original function. Remember the domain, the x cannot be, and the x is in the denominator cannot equal 0. To find the range, it's going to be the values where we will have a numerator that actually works. So to find the domain, you're just going to set the denominator equal to 0 and say it cannot equal 0. Solve for the x, and we find that x cannot equal -2. To find the range, we find the numerator and do the exact same thing. We say it cannot equal 0. Then we're going to solve for x to see where our range can lie. So our numerator cannot equal 0, so y minus 1 cannot equal 0. If we solve that, we would get x cannot equal 1, but we're actually talking about the range. So the range is your y value, so we change that to a y, and y cannot equal 1. Since we do have a restriction here, when we get done and we find the inverse, we will know that the domain of your inverse will be x cannot equal 1. Remember, to find your inverse, you first get rid of the f of x, replace it with a y, and then you're going to switch the x and y values. So we've written y instead of f of x, and we've switched the x and y values. Now when you want to get the y by itself, the first thing we're going to do is try to get rid of that denominator. So we're going to multiply both sides by y plus 2. So after we multiply both sides by y plus 2, these are going to cancel on this side, on the right side. On the left side, we can distribute that x. So x times y gives me xy. X times 2 gives me 2x. And on the right side, you're just left with y minus 1. Now we want to get all the y's to one side, everything that doesn't have a y to the right side. So I'm going to subtract the y to the left and subtract the 2x to the right. Once you have all the y's on one side and everything that's not a y on the opposite side, we do need to get the y's out, so we can factor a y out from both pieces on the left. If we factor out a y on the first part, xy divided by y is just going to leave you with x. And negative 1y divided by y will just leave you with negative 1. Now that we have the y by itself, we have y times the quantity x minus 1 is equal to negative 2x minus 1. This is multiplication, so we can divide on both sides. After we're done dividing by x minus 1 on both sides, we will be left with y is equal to negative 2x minus 1 over x minus 1. The last thing you have to do is replace that y with the inverse function of f. And then just state your new restricted domain. Remember, it has to match the range of the original. So our domain is going to be x cannot equal 1, which does make sense because the denominator can never equal 0. And that would give us a denominator of 0 if 1 minus 1 in the denominator. If you're given two functions, f and g, an inverse function can only exist if and only if f of g of x is equal to x and g of f of x is equal to x. So where x is located in the function of f, you replace it with g and you simplify, you should get x. And if you take g of x and replace your x with the function f of x, you should still get x. So if these are two functions, the first thing we're going to do is find f of g of x. This means where our x is located in our f of x function, we're going to replace that x with the entire function of g of x as stated. Now we're just going to simplify. We can get rid of those parentheses, and positive 4 minus 4 just gives us 0. We can change that numerator. Instead of just being 6, we can write that as 6 over 1, and then we'll have a fraction over a fraction. When we have a fraction divided by a fraction, we can flip the second one and multiply. So we can change that to 6 over 1 times x over 6. Once you have that written out, we can cancel. So the 6's will cancel each other out. And so you'll just be left with x over 1, which is equal to x. So it works for f of g of x. Then you just need to check to see if it works for g of f of x. So in this instance, where we have our x on our g of x, we're going to replace it with the entire function of f of x. The first thing I want to do is make that numerator a fraction. So I'm going to make that 6 over 1. So then we have a fraction divided by a fraction. When you have a fraction divided by a fraction, you can flip the second one and multiply. Now we can cancel across. I have a 6 on top and a 6 on bottom. Those will cancel. That's just going to leave me with x minus 4 over 1, which we can just simplify to be x minus 4. And we combine like terms. X minus 4 plus 4 will just leave us with x, which is what we were wanting. So this is an inverse function.